All right, this lecture involves Gibbs free energy. The symbol for it is G. And G is defined as H minus Ts. So this is the enthalpy H minus temperature in degrees Kelvin multiplied times the entropy. We are usually interested in the difference in Gibbs free energy from some state to another. And we use delta for that. Delta G is going to be equal to delta H minus T delta S. This is a very well-known equation here. And we can use it to think about what Gibbs free energy means. So there's three parts to it. The first one would be the enthalpy. This is going to be associated with the chemical reaction that's taking place, for example. Where does the energy come from in a chemical reaction? You have the bonds of the reactants are broken, new molecules are formed, and new bonds are formed, and different bonds and molecules have different amounts of energy, and there's always some kind of difference. Sometimes energy is absorbed, lots of times energy is given off. So endothermic and exothermic. So this would be the heat of the system, your chemical system or some mechanical system. And then the temperature we know, and then the entropy here is going to be the part of the system that's disordered and can't produce useful energy. So some of the energy that comes from this system then is not useful work, and delta G is associated with the work that's available, the energy that's available to do work. So the T delta S term would be the part of the system that is disordered. In other words, the system's produced heat, and then the heat dissipates and can't produce useful energy, like friction, for example. Okay, so the difference between those two, so there's the heat available from the chemical reaction. Let's say some of it heats up some part of that system where the energy is just dissipated. That would be your entropy consideration there. And then the difference between them is the free energy. And this is the energy left over that's available to do work, or the difference between the two, you could say, that's available to do work. And in turn create disorder. All right, so if we want to know if we've got enough energy to move a car down the road using gasoline and a battery and all the mechanical parts of the engine and the car, we have to know how much energy this is going to be, the Gibbs energy we'd be interested in. So I have a few examples here. Let me talk about those. And the first one would be the car engine. It's kind of an interesting one. You have the situation where there's a piston. You have pistons in the car engine and they move up and down. The piston contains a space where gasoline and oxygen, or air I should say, gasoline and air, and hence the oxygen in the air, are contained, and the piston moves up and down. So the reaction that takes place, you got octane, C8H18, that's a liquid. And this is reacting with 25 halves or 12.5 moles of O2 gas to form 8 CO2 gas plus 9 H2O gas, which eventually becomes liquid when it cools down. But, you know, octane is just one component of gasoline. Gasoline is a mixture of different hydrocarbons. It's just one of them. And this is the combustion or the burning of the octane. Notice you get CO2 here, which is the subject of climate change. So anyway, what happens in the engine, you have the piston that moves up and down. When the piston moves down, it compresses the gas mixture, or I should say the octane mixture. Then you have the spark plugs getting electrical energy from the battery. They ignite the octane mixture, which causes the piston to compress. I can't remember which way it goes. I guess it's going up to expand. Yeah, once it's ignited, then the piston expands. So it causes it to expand. And then at that point, the expanding piston is coupled to the crankshaft, so it turns the crankshaft. And then the crankshaft is, the piston is moving up and down, and it's causing this crankshaft to turn, which then is connected to the powertrain. This is way more detail than you want. Powertrain, A-I-N there. And that starts turning, and it moves from the engine down into the axles. So axles are next, and then they turn the wheels. And your car goes down the road. So two types of energy associated with the car engine. You have the energy, so there's heat. The heat is the energy needed to do all of that. And, you know, some of that energy gets dissipated in all that. Your car engine heats up, right? But how much is available to do work? How much energy is available to do work? And so that's delta G, the Gibbs free energy. And so that's always a topic associated with that. And then, of course, the battery is providing energy to do all kinds of things, not only influence the spark plugs, but turn on your radio and your heater and all those things too. So anyway, a lot of that heat gets dissipated, and you know, if you study thermodynamics in detail, you realize that it's impossible for all of that energy to be converted to work. There's always this other part of it. So that's one example. And then let's see, another example here would be, well, just a battery in general. We can think of something simple like zinc and copper forming zinc 2 plus copper solid. So there's a chemical reaction. It's an electrochemical reaction. We're going to study this in detail coming up next chapter. In fact, that's a parenthesis there. Next chapter will be electrochem. So there's energy associated with this. You've got, 0 is the oxidation number for zinc, and then it's going to +2, so that's going to be the oxidation, and then the reduction here would be the copper 2 taking up those electrons to make copper solid. And, just a simple, you could put a light bulb in the circuit here. This is wired up, right? So you got the electrons moving through the wires. You could light a light bulb. You can do anything with that battery. You can spark your spark plugs for the car. So anyway, we'll get to that. But there's free energy to be considered there. And the other example was just this example of muscle contraction. And muscle contraction involves two fibers that rub back and forth against each other. and one is called myosin, and the other is actin. Oops, that's an N there. They move back and forth, and for the contraction, you know, the myosin and the actin separate, and that initiates that process. And so it's kind of a cycle of attachment and detachment of these filaments. And then during the detachment part, that's when the muscle can contract. So energy is needed for muscle contraction. So muscle contraction needs energy. And where does that energy come from? So the energy, or the free energy, comes from the reaction of glucose plus ATP. Now ATP is going to be stored in these cells, in this tissue, and or fibers, I should say, and it's just kind of a small amount of ATP that's available. After that, it is chemically generated in time during the process, and so the reaction here gets things moving, and this glucose plus ATP forms glucose 6-phosphate. That's a 6. Plus ATP gets converted to ADP, and then there's H plus formed as well. And delta G for this reaction is really well known. If you go to your biology books, you'll see this number here. Delta G for this reaction is negative 16.7 kilojoules per mole. And as is always the case in biology, there's all kinds of reactions coupled in, every reaction doing something different, and so it's never easy to talk about this stuff. But anyway, this is an important number there. This is from that reaction. The amount of energy that's needed for the muscle contraction is negative 16.7 kilojoules, and that would be per mole of ATP. All right, just some ideas there. Whoops, of delta G. So now we will go ahead and look at some details here, and the first one has to do with a graph, and it kind of gives an idea about G and the process of a chemical reaction. So if you plot G, the free energy, versus what's called the reaction coordinate, which means this is going to be delta G for the reactants on the left-hand side, and then for the products on the right-hand side. And so you're looking at this process of reactants, all the energy changes during the process of reactants forming products. And so this is not delta G, this is a G that we're plotting. And you could say, you know, maybe some number associated to this point on the graph would be the sum of all the energies available for the reactants, the free energy. And then you would maybe put another one over here, which might be if it's an exergonic reaction. So with G, we use the terms exergonic and endergonic. So if it's exergonic here, then the G for the products would be less. So you might say, okay, well, it's just going to be some linear relationship here. It just decreases from, you know, reactants to products, but that's actually not the case. And so you look in time during this process, and you find that it's kind of a curve going down, hits a minimum, and then comes back up like that for the products. So you wouldn't necessarily have expected that, but that curve has a lot to do with entropy and mixing, things like that. You can see that if you look in detail at some of the thermodynamic equations for that. So what does this mean? Okay, first of all, the minimum here is associated with equilibrium. And you can start with the reactants, and they're going to eventually move to a lower and lower free energy until it hits this minimum. Or you could start with the products, same thing. They're going to move in the opposite direction until they kind of hit this minimum here, or till it hits a minimum. And so oftentimes we're interested, well, first of all, the difference between these two is delta G for the reaction. This is something, you know, if you had the little zero there, standard state, you could use the tables, the tabulated values of delta G and the thermodynamic tables, and you could calculate, just like I showed you for entropy in the last video, you know, products minus reactants kind of thing. Then that's delta G standard for the reaction. But the other thing you can look at is how is delta G changing over a short period of time. So this would be delta G non-standard. This is not for, I mean, the reaction's proceeding, but we're not there yet. It's related to Q, QC, if you remember that from equilibrium. So the value of Q is changing as the reaction proceeds towards equilibrium. So in other words, at every step, you can look at the difference between this stage of the reaction from here to here, and there's a delta G associated with that, and then another one, and another one. So it keeps going down, and then finally when you hit the minimum, there's no change anymore. So that's going to be associated with this delta G being equal to 0. Okay, that's a complicated subject, and lots of things going on here. Oh, also, if that's at a minimum, I think I said that, so delta G would be equal to 0. All right, so the equation that we use for this is delta G is equal to delta G. You can say for the reaction, you can put that in Rxn for the reaction. So delta G for the reaction at any step is equal to the standard delta G for the reaction, as I've defined it, plus RT log Q, and you can write QC, doesn't, whatever type of Q it is, it's not so important. Okay, and so this is the reaction that's describing, and also, by the way, you can look at delta G differences going that way as well, from products going back to the equilibrium situation. Didn't mention that. All right, so then when you hit the minimum, when the system's at equilibrium, delta G for the reaction is not changing, it's just constant. And so that is going to be 0, and this will be equal to delta G for the reaction plus RT log, let's see, when it's at equilibrium, then QC becomes KC, right? Or you can just say K. And then you solve for delta G reaction, and that's going to be negative RT ln K. I'll leave off the C there. I'll just say log K. So this is one of the very important equations in thermodynamics because it shows you that there's this amazing connection here between what? Between the equilibrium constant and delta G. All right, so, you know, it's interesting. It's like the relationship between information in 2 chapters, there's that. But, you know, if you know something, if you know the value of the equilibrium constant, you can calculate what delta G is for the reaction. That's pretty astounding, and then vice versa. So there's going to be 3 equations like this. 2 of them are going to come up during the next chapter on electrochem. You'll see a real interesting connection between those. All right, so then the other comment is that as the reaction proceeds, delta G gets smaller and smaller until finally the energy is unavailable to do work. So energy is being given off during the process, and then it just settles down. All right, that is an interesting graph, and we'll probably come back to that a little bit later. So then the next topic has to do with using the equation for delta G, and we want to be able to predict spontaneity in a process. So this is a little bit tricky here. So we want to use the signs of delta H and delta S to predict spontaneity. Oops, that's an O. Spontaneity. All right, now in thermodynamics, we use the word spontaneity twice. One of them has to do with delta S. So, if we have a perfectly ordered deck of cards, we shuffle them, and now we have a disordered deck, right? That is a spontaneous process. What's the probability that you're going to shuffle the cards and you're going to end up with a perfectly ordered deck? That probability is so low compared to all the other ways that those cards can combine. So we say, yeah, so the process of the cards becoming disordered is spontaneous. And when we say delta S is positive, we say that means that it's a spontaneous process, right? So we use spontaneity when we talk about entropy. And that's all about just creating disorder. But we also use delta G. We use the word spontaneity again for delta G. So when delta G is negative, the process is spontaneous. When delta G is positive, it is non-spontaneous. So there's that word spontaneous again. And it means something different here. We're not just talking about whether something's going to be ordered or disordered. Here we want to know, will the chemical reaction happen or not? If the reaction is going to happen, if it's going to proceed forward, then delta G will be negative. And if you mix things together, nothing happens energetically, then that's a non-spontaneous process, and delta G there is going to be positive. So that's pretty confusing, right? You have delta S being positive for the spontaneous process. Then you have delta G being negative for the spontaneous process. But we're talking about two different processes. For entropy, it's creating disorder. For Gibbs free energy, it's about will the reaction happen or not. So hopefully I give you a sense of that anyway. But watch for that. People confuse that. So now this is the other one more point about this, I guess, is that if delta G, let's just get rid of that line. Okay, so the third point here is if delta G is 0, then the system's at equilibrium. All right, that was the third point. Okay. All right, so I want to show you this chart, and we want to compare what's going on with delta H and delta S. Whoops. The difference between them is delta G. Okay, so we can consider several different situations. If the enthalpy of the reaction is negative, that means heat's given off. And if the entropy change is positive, that means there's going to be some spontaneity associated with that. We want to figure out what the sign of delta G is going to be. So bear with me here. Let me do it down at the bottom. So if delta H is negative and you're subtracting the absolute temperature, Kelvin, which is always positive, and let's say the entropy change is positive here, which means there's disorder, right? Then you've got a negative and you're subtracting something positive, and so that will give a negative value for delta G. So you're adding, how do I say that? You're adding something, you're subtracting something positive here. So that's going to make this negative right here. All right, then next we have the situation where delta H is negative, but the entropy is negative as well. Okay, so this one's a little bit different. So delta H is negative, and then you're subtracting, your Kelvin temperature is always positive, but now you're subtracting the entropy change, which is negative, right? So you've got a negative, and you're subtracting a negative, which is positive, right? So this is a negative, and that you could say you're adding a positive, adding a negative times a negative. Everybody has their own way of saying this, which makes it difficult. So the question is, which one will it be? So is delta G going to be negative or positive? And it has to do with the size or the magnitude of these two terms. So if the value on the left here, let me get my pointer. So if this value, this negative value is larger, or the absolute value of that. If the magnitude of this negative number is larger than the magnitude of the positive number, then it's going to be negative overall. So this would be negative. So then what would be the situation? Come back over here. What would be the situation where delta H would be negative? That's exothermic. And then the positive, this positive term here would be smaller. And that's going to be the situation when the temperature is really small. Okay. So in other words, the temperature here, which is positive, if this is a really low, like 10 degrees, that's an over exaggeration, but just some very low temperature, maybe 0 degrees C, something like that, then this is going to be small. It'll make the whole term small, which means this term will be small. And so the enthalpy term will predominate. Now, in the other case where the temperature is high, so if this is high, that's going to make this entire term high because this is high. Then you're subtracting a negative, so then the positive term will be greater than the negative term for delta H. So you've got that it's going to be negative at low temperature, and it's going to be positive at high temperature. And what does that mean? So if, let's go back to the first example. If delta G is negative, then this is going to be spontaneous. If delta G is negative in the second example, it'll be spontaneous. The reaction will occur as long as the temperature is low. And it's a very odd example here because you're going to heat up your system. You're going to increase the temperature. The delta G value is going to become positive. And basically the reaction shuts down. It'll be non-spontaneous. This is for delta G right here. All right. All right, so then the next example is positive, positive. So in the case of positive, positive, let's look at this again. Scrunch it down. So for this one, your delta H value is positive. You're subtracting a positive temperature, and then the value of delta S is positive, right? So you've got positive. So you've got a positive, and you're think of it as adding a negative or a subtraction term. So you got the same situation again, which is larger, okay? At low temperature, let me use my pointer here. When the temperature is low, then this term will be low, really small compared to this term. And so it's going to be positive at low temperature. And then when the temperature is high, then this whole term is larger than this whole term. And so it'll be negative instead. So which one is larger? That's the issue here. Excuse me. So in this case, it's going to be positive at low temperature, and negative at high temperature, which means it'll be non-spontaneous at low temperature and spontaneous at high temperature. And that's really what we're most familiar with. So we start out with a reaction that's not doing too well at low temperature. We add some heat to it, and then all of a sudden it's much more spontaneous, and you can carry out your reaction as you wish, as you want it to be. And then finally you can look at the case of positive negative. So in that case, positive negative, you've got positive and you're subtracting a positive temperature times a negative entropy. And so you're going to subtract a negative. This is going to be positive in every situation. So positive means that it's going to be non-spontaneous. That means the reaction will not occur. And believe me, I get a lot of questions on this. It seems kind of simple here, but it gets a little confusing as well. So feel free to talk to me about this. You can ask questions on this during our discussion sections there. All right, that's pretty useful material, because you can just kind of quickly guess, you know, whether something's going to be spontaneous or not. All right, now we can look at calculations using thermodynamic data using the table. So calculations using thermodynamic tables. And for this example, I think we looked at urea earlier in the last video, but we'll do it again. NH3 here in the gas phase reacts with CO2 in the gas phase, forming urea, which is NH2CO, NH2 solid, urea plus water, liquid. Okay, water. And if you go to the tables, you're going to see these S values, delta H values, delta G values. They're going to be columns for these, but I'm going to write them in rows. So I pulled these numbers from the tables. Now you don't have delta S values because absolute entropies can be calculated. I showed you how to do that. Well, you're not going to be doing a calculation, but I showed you the graph and the potential that you could calculate the absolute value associated with 298 Kelvin. So those numbers are 192.5, 214.0, 104.6, and 70.0. These units are joules per Kelvin. Then you would pull the delta H values. Now, why is it delta? Because you don't know the absolute enthalpies, right? And the delta H values, the enthalpies are always calculated relative to a standard state. So let's not spend too much time on that. These are going to be given in kilojoules per mole in the tables. So you got joules for entropy and kilojoules for enthalpy, so watch out. So this is minus 46.1, negative 393.5, negative 333.5, and negative 285.8. Alright, and then you also want the delta G values. So those are tabulated, and those are kilojoules per mole as well. And here you have negative 17.0. And negative 395.0. Urea is negative 199.1, and then water is negative 237.0. So then, for this reaction, the formation of urea, we can calculate delta G for the reaction. So that's our question. What is delta G standard for the reaction? And there's two ways to do it. One is you can use delta G is equal to delta H minus T delta S. And the other way to do it is to calculate delta G directly from products minus reactants. So there's two ways to do it, and let's do them both because sometimes you need to kind of know your values of delta H and delta H separately, and sometimes it doesn't matter. So it just depends on, it's good to know how to do it both ways. All right, so then in order to use this equation, we have to calculate delta H first for the reaction. And it's going to be products minus reactants, and you're multiplying times the coefficients. They're all 1 except for ammonia. So delta H then is going to be negative 333.5 plus a negative 285.8. So that's for the products. And then you're going to subtract for the reactants. You got to multiply times 2 on the ammonia. So 2 times 40, make sure I got the right one. 2 times negative 46.1 plus 1 times negative 393.5. So those are the reactants. All right, and so then delta H, you go through all of that. Delta H for the reaction equals negative 133.6 kilojoules per mole. So that's enthalpy. Now you do the same thing for entropy. So delta S reaction, RXN there. You just similarly take the numbers out of the table. I scrolled them out, but you can look at that. 104.6 plus 70 minus 2 times 192.5. Whoops. 192.5 plus, yeah, I did in parentheses there, plus 214. So delta S for the reaction equals negative 424.4 joules per degree Kelvin. And here you got joules and kilojoules. You're going to combine them in the equation. Delta G is delta H minus T delta S. So you got to either go to joules or kilojoules, you know, one way or the other, but we'll go to kilojoules in this case. So this is going to be negative 0.4244 kilojoules per mole. And this is really important per Kelvin, sorry, not per mole. Well, it's per Kelvin per mole. Sometimes I leave that out. I'm kind of messy about that with my entropy. Probably a good idea to put that in. Mole, per mole, and per mole. Lost my train of thought there. I don't know. So delta G for the reaction equals delta H, which is negative 133.6 kilojoules per mole, minus T delta S. So the temperature, since it's standard, this is going to be 298.15 Kelvin, times the entropy, which is negative 0.4244. And this is going to be kilojoules per mole per Kelvin. Like that. I hope I got that right. Yeah, okay, joules per mole. All right, so you put it all together, and So delta G for the reaction is negative 7.13 kilojoules. Negative means spontaneous. More to say about that in a moment. All right, so then method 2, this would be method 1. Okay, method 2 is way easier, but just depends on what you need. And you can just use delta G directly. So delta G here for the reaction will be, and I'm taking the numbers out of this row here for delta G. And this will be equal to negative 199.1 plus a negative 237. Okay, so that's products, delta G for the products. And then you're subtracting delta G for the reactant. So again, times the coefficients, 2 times negative 17 plus a negative 395, like that, for the reactants. All right, that turns out to be negative 7.13 kilojoules per mole. You get the exact same answer. You better, right? That's the thing about thermodynamics. It's just every single aspect of it is consistent with every other aspect of it. It's just so absolutely systematic. Everything can be derived from scratch, and it's just one thing. Everything about entropy is consistent with everything about free energy and so on. All right, well, look at that now. We calculated delta G 2 different ways, and the negative means that it's going to be a spontaneous process. So more on that later. And now, I guess we can keep going. I don't know, maybe we should stop here and I'll make a third video.